Hello everyone, this is Tai from Instantaneous Education. In this video, I will help you to answer the most difficult questions in IB Physics Paper 1 HL, May 2019. This is the first question. A student measures the radius R of a circular plate to determine its area. The absolute uncertainty in R is delta R. What is the fractional uncertainty in the area of the plate? So the question is the fractional uncertainty. So we definitely know that this is the question in the topic about uncertainty and measurement. This is the measurement of the area of a circular plate, and we measure that area by measuring the radius of the plate. The equation for the area of a circular plate is A equal to pi r squared, where r is the radius of the plate. According to the knowledge about fractional uncertainty, we have that the fractional uncertainty delta A over A is determined by 2 times the fractional uncertainty of radius delta R over R. Why? Because we can consider R squared is the product of R and R. The fractional uncertainty of a quantity which is a product of 2 or 3 quantities is the addition of the fractional uncertainty in each quantity. So here we have the square of the radius, and we move that square, the power, to the factor of the fractional uncertainty, and therefore the answer for this question is answer A. Now let's move on to the next question. Question 2. A proton has momentum of 10 to negative 20 Newton seconds, and the uncertainty in the position of the proton is 10 to minus 10 meters. What's the minimum fractional uncertainty in the momentum of this proton? And we have 4 options. So this is also a question about fractional uncertainty, and it is the uncertainty about momentum and position. These 2 terms probably will remind us about the relation of uncertainty of these 2 quantities. This is called the Heisenberg uncertainty principle. A German scientist in the early of 21st century, Heisenberg. This principle states that the absolute uncertainty in momentum multiplied with the absolute uncertainty in position of a particle, a tiny quantum particle, is always greater than or equal to the Planck constant h over 4 pi. H is the constant that's given in the data booklet, which is 6.626 times 10 to negative 34, and I don't mention the unit here. The meaning of this uncertainty principle is that when we measure both quantity, momentum and displacement, we always have a limit of precision. We always have some uncertainty in the measurement. The more precise we measure the momentum, the greater the error we measure its position, and vice versa. The more precise we measure the position of the particle, it's harder to determine the momentum of the particles. Okay, now we can do some approximation so that we determine the answer. The uncertainty of positions given in the problem, delta x, is 10 to minus 10. And the question is delta p, okay? So this product must be greater than this number, 6 times 6, 26. You don't have to remember this number. It is in the data booklet. But the point is pay attention to the power 34 here, divided by 4 pi. Just focus mainly on the power. 4 pi is 3.14 So 4 times pi is about 12, and 6 divided by 12 is about 0.5. So about, this is just an approximation, okay? Times 10 to negative 34, and we can rewrite it like 5 times 10 to negative 35. Note carefully on this power. So in order to get minus 35 power on the right side, on the left side we already have minus 10, so the power of the uncertainty in momentum has to be minus 25. So we can determine that uncertainty in the option A, okay? So that's how we can do the estimation without using the calculator in this paper. Now, let's move on to the next question. This question is about momentum and force. The graph shows the variation of momentum with time for an object. So we have this diagram. The momentum increases linearly, a straight line from 0 to 20, and then doesn't change at all, a straight horizontal line here. What net force acts on the object for the first 2 seconds and for second 2 seconds of the motion? So in order to answer this question about momentum, and the question asks us about the force, we have to recall the relationship between force and momentum. We know that the net force is the rate of change in momentum, delta P over delta T, rate of change in momentum. Okay, remember that term, very important. That definition, rate of change in momentum. So to calculate the net force for the first 2 seconds, for this part of this diagram, in the first 2 seconds, the momentum increases linearly, gradually, with the same rate, which means the net force is always the same during the first 2 seconds. So to calculate this rate of change, the increase in momentum is 20, because the final momentum is 20 kilogram meter per second. And the initial momentum is 0, so the increase is 20 kilogram meter per second, and then divided by the time, which is 2 seconds, and we get 10. The unit is kilogram meter per second again, which means kilogram meter per second square, which is the unit of force Newton. So it is definitely the right equation. So the answer for the net force is 10. So we have the two options A or C, and we eliminate two options B, D. Now, the next part, the force for the second 2 seconds, which means the instantaneous force here. Instantaneous force. It is like instantaneous acceleration. It is also defined as the rate of change momentum. But here, starting from 2 seconds, the momentum is constant, doesn't change anymore. So the rate of change momentum at this moment is 0, and therefore the force at this instant is 0. So the final answer is A. Moving on to the next question. This is a question in thermophysics related to ideal gas equation. Cylinder X has the volume V and contains 3 moles of an ideal gas. Cylinder Y has a volume of V over 2 and contains 2 moles of the same gas. The gases in X and Y are at the same temperature T. The containers are joined by the valves, which is open so that the temperature do not change. What is the change in pressure in X? We initially have 2 containers, one container of the volume V, and the number of mole initially 3 mole. Another cylinder which half volume of that, which has 2 mole. There's a valve, and we neglect the volume of the valves, and they open the valve so that the gas can move from one container to the other and mix together and become one amount of gas with the same pressure in both containers. So in order to find the change in pressure in X, we call P1 is the initial pressure of 3 mole of gas in the first container X, and P2 is the pressure in the second container Y. In order to answer this question, we're going to use the ideal gas law equation. Now, let's write the two equations for the two containers. The first container pressure P1, volume V, the number of mole is 3 moles, and multiply with the gas constant R and temperature T. The second container pressure P2, volume V over 2, the mole number 2 moles, and then RT. Let's write a third equation when the two amount of gas mix together. The gas in the two containers, after mixing with each other, they have the same pressure, and the total volume of the two containers is V plus V over 2. The total number of mole, of course, 3 plus 2. And the gas constant doesn't change R, and the final temperature stated in the problem that this is a constant during the process, no change. So the question is to find this final pressure P. In order to do that, we will convert these equations a little bit. From the first equation here, we deduce that RT equal P1V over 3. Now, plug this RT into the third equation. We get 5 times P1V over 3. Or we can write 5 over 3 P1V. Now, on the left side of the equation, we have P times 1 plus 1 half is 3 half V. And we can cancel out the V in the two sides of the equation. And then derive the equation a little bit to get P, okay? Because the question is P. So we get P equal 5 over 3 divided by 3 over 2, which means multiply with 2 over 3. P1. Which is 10 over 9 P1. So P is 10 over 9 of P1, which means that it is P1 plus 1/9 of P1. Agree? 1 plus 1/9 is 10 over 9. So this 1/9 P1 is the increase in the pressure in the cylinder in the container X. Now, in order to get the result that is similar to one of the fourth options, we have to find the relationship between P1 and RT from the first equation here again. P1 is 3 times of RT over V. And now add this thing, this P1 in here, we will get the final answer. Okay, so the increase in the pressure, delta P equal 1/9 of P1, and because P1 is 3 RT over V, then divided by 9, we divide 3 by 9, and we will get 1/3 of RT over V. So come back to the fourth option. We see that the option A is the thing that we choose in accordance with our calculation. And because this is the increase, the rise in the pressure, so it must be a plus, not a minus, okay? And that is 1/3 of RT over V. So you see that it takes some steps, some thinking and variation of the equation so that we get the final result. So the advice when you're doing this paper is that to leave this question later if you spend a minute and don't know how to get the answer. So spend time on it later, okay? Moving on to the next question. The next question, 16. An object at an end of the spring oscillates vertically with simple harmonic motion, SHM. The graph shows the variation with time of the displacement x of the object. So we see that the displacement x starts from -2a and then increase to 0 and increase to the maximum positive 2a and then decrease back. This is a sine or cosine equation. Depends on how we can write the equation to describe this oscillation. And the question is the velocity of the object. In order to answer this question, we just do as follow. The initial position at time is 0. When we start the clock to record, to describe the motion, the x is -a. It is at the negative maximum displacement and it's moving to the equilibrium position, moving in the positive direction, which means the velocity must be positive, and it was initially at the maximum displacement, so the initial velocity must be 0. So it must start from 0 and then increase. So if we plug the time t is equal 0 in the 4 option A or B or C or D, we will get, when we plug into C and D, the cosine of 0 is 1 and therefore we will not choose C and D. So that leaves A and B. And if we plug the time t, which is very small, like 0.01 second, into the one of the two option A or B, we see that sine of a very small angle is positive. So, and the velocity here must be positive after the time, a very tiny time interval after 0, after when we start the clock. So in order that the velocity is positive right after moving away from the greatest negative displacement toward the equilibrium in the positive direction, option, the answer must be B. That is how we answer this question quickly. But if we want to understand this problem better and recall all the knowledge in the section about simple harmonic motion, let's write the equation to describe the displacement and velocity of this oscillation. Starting with x, the equation for x is x equal the amplitude, which is 2a, multiplied with sine or cosine. We can choose sine or cosine. And in order to test if our answer B is correct, and remember that velocity is the derivative of displacement with respect to time, then we would choose x to be a cosine function, so that when we take the derivative of cosine, we get the sine function. Okay, so that is cosine of omega. Omega, the angular frequency, omega is 2 pi over t. And period in this problem is from here to here. The period is 2t, not 1t, as usually in other problem. This problem is a little bit special because the period is given on the graph is 2t. So that is 2 pi over 2t is pi over t. Angular frequency here, pi over t, multiply with the time t variable, and then add it with the initial phase. The initial phase must be a value so that when the time t is 0, the cosine of the initial phase, let's call the initial phase phi, okay, cosine phi must be -1. So pi here must be pi. Or I can write equation as minus 2a times cosine of pi t over t. Instead of writing the initial phase pi, I will replace it by a negative sign here. Okay? Now, the derivative of displacement over time is velocity. The constant minus 2a stay the same. Derivative of cosine is negative sign, negative, so another negative. So the minus sign becomes a plus sign. Okay? And sine of pi over t times t. And do not forget that this is a variable u, not just variable x. Normally in math, it is a combined function. So when taking derivative, we also need to take the derivative, multiply with the derivative of this variable. Pi over t is the constant left after taking derivative. So that we can move the constant pi over t here to the front of this. So that is 2a pi over t sine pi over t times t. So that is exactly the equation for the answer B. Now let's move on to another question. Question 18. Unpolarized light is incident on the two polarizers. The axis of polarization of both polarizers are initially parallel. The second polarizer is then rotated through 360 degrees as shown. Which graphs show the variation of the intensity with an angle theta for the light leaving the second polarizer? Okay, to answer this question, we need to read it very carefully and note the important information. The incident light is unpolarized light. So after passing through the first polarizer, its intensity will always decreases by half amount. So let's assume that the I0 is the initial intensity of the incident light. After passing the first polarizer, its intensity will decrease to I0 over 2. Always after passing through the first polarizer, the unpolarized light will become a linear polarized light, which means that now it has only one direction in which the electric field varies vertically along the polarizer axis. And later, when it goes to the second polarizer, it reduces its intensity, and the second polarizer is rotated slowly. And after that, they use a sensor to measure the final intensity of the light passing through the second polarizer, and this intensity varies as a function of time with the change in the angle between the incident linear polarized light coming to the second polarizer and its axis of polarization. And the intensity after passing through the second polarizer is I final. Let's call it is I. It is described by a law called Malus law, which states that the intensity of the light after passing through a polarizer is the incident intensity, which is I0 over 2, because that is the intensity after passes the first polarizer, multiply with cosine square of the angle between the incident light on the polarizer 2 and its axis of polarization. So this is a square of the cosine function, and when we plot the graph of this square cosine function, we will have a graph like the option B given in the thing that we have to choose. So B is our answer. Okay, let's see. if we can plot that graph, of course you can replace some value like 30 degrees, 60 degree, 90 degree, 180 degree, and so on to plot the graph. It takes time. But if you are pretty good at trigonometry, then you can quickly solve this question. So when I use a graphing calculator, a software to plot the graph of the cosine square of a function with the variable x, and here I choose 2 as the magnitude of this function, and it's just any arbitrary number that I choose to illustrate the shape, how the graph look like. Okay, and let x, which is the angle theta in our problem, the angle between the incident line and the polarization axis, varies from 0 to 2 pi. It looks like a W letter. It's like a wave with 2 period, okay, 2 wavelengths. So our answer is B.